So the first method is Euler's method. Okay, and we'll just consider the simple equation with one variable. By one variable, I mean there's only x and there's only a single variable y. So when we specify this kind of problem, we also need to be given the initial condition. So at x equals x0, what is y? So y is y0. Okay, an example of where you might see an equation like this. One example is dv dt equals a. So here you're saying that the rate of change of velocity is acceleration. So kind of famous kinematics equation. Okay, now you've done this problem if a was constant, right? It's very easy to solve it, right? V equals at. But if you're given a is some function of v, let's say sine of v or sine square v or cosine v, now it becomes a little bit harder to integrate it. It's still doable. If I give you log of v, even harder, right? Tan v, whatever. So you could have a very function of v and then becomes something which you cannot do by hand analytically, but you'll have to use some kind of a numerical method. So let's see how to solve this equation. So what we'll do here is the following. We'll choose some step size, okay? So that is how much we want to increment the value of x to find the value at the next time step, because ultimately, in this case, y is a function of x. So we know the value at x0. We need to find the value at the next interval. So we'll have these grid points, x0 plus I delta x, where I goes from 0, 1, 2, so on till n. So to give you an idea what this means is if you take the x-axis, and let's say this is x0, then you'll literally divide this into grids. Each of these lines are dx apart. So this is going to be delta x, same here, delta x, and so on. So this value here is going to be x0 plus delta x when I equals 1. This will be x0 plus 2 delta x, and just so on. It just keeps going. Okay, and then when we are trying to do this, so this is y. We know the value y0. Let's say this is, so we're given y0. That's the value here. So this is known. And then what we are trying to do here is we're just going to try to march along. We'll try to figure out what is the value at this grid point and then this grid point, right? So this is something which we'll get from the Euler's method. So this is how Euler's method proceeds. So how do you get the values for y? Well, you would just use calculus. So calculus tells us that dy dx equals f of xy can be approximated as follows. Okay, so there is a definition for dy dx, and this is something which we have done in the past for numerical differentiation. What is an approximation for dy dx? One approximation is the forward difference. So you substitute y dy dx as yi plus 1 minus yi divided by delta x. Okay, you also have a backward difference and a central difference. Let's just stick with forward difference. So this will be equal to f of xi yi. Forward difference formula. Okay, now that we have this formula, we can solve for yi plus 1. So y I plus 1, you'll have to move the delta x on the other side, and then you'll get delta x f of xi yi. Okay, so this formula is known as the Euler's method. So you know what the value at yi is. In this case, I is 0. So you know the value at y0. You know f of x0, y0 because you're given the function. So you can compute y1 and then repeat for y2, y3, y4, so on. So you'll get the whole trajectory. Yes, so there's that thing, and then there is something called truncation error, which we should really be worried about always when we look at these expansions. So when we are actually doing this formula, what are the errors introduced? And that's going to be important if you're trying to uh, lay grips on how accurate is a calculation. So this, by the way, comes from the Taylor series. So Taylor series tells us that yi plus 1 is yi plus delta x dy dx plus delta x square divided by 2 factorial t square y dx square plus so on. But this is nothing but delta x. The dy dx is nothing but f of x comma y plus, so everything here after this is ignored. Okay, because you can see that this formula which I wrote down here is exactly this. So that part is taken by the Euler's method. Everything else is ignored. So we can say that the order of error is about delta x square. We can see it's the leading term. So when you are talking of the truncation error, it is nothing but yi plus 1 minus yi minus delta x fxi yi, literally moving things around. And you can see that it's order of delta x square. So let me abbreviate the truncation error as TE. The truncation error is of the order of delta x square. Okay, so it says that the smaller is delta x square, the better you are. So if you choose the delta x, what's delta x? Delta x, if you go back, it's basically the step size, right? This is delta x. How fine you're making the grid. Now, if you make it 0.1, your truncation error is 0.1 square, 0.01, so accurate to 2 decimal places. If you instead go for delta x as 1e negative 2, 0.01, then delta x square is 1e negative 4, so you have 4 decimal place accuracy. So that's the truncation error. There's something called total error, which if you want to find the total error, you take the truncation error and then you integrate the truncation error over the entire time span. So it's almost like taking total error dx, the integral. So it turns out that the truncation error is delta x square, and then this dx is basically the step size. So when you integrate this, you literally get integral dx, and that comes out to be approximately the number of grid points. Okay, so because you're integrating over the entire span, but the spacing, this is literally proportional to 1 divided by delta x. And so the total error is actually delta x. The total error is always worse than your truncation error, because when you take the total error, you are summing across the whole period. So total error is even bad. So you and really care about total error. When you're doing integration, you want to see, if you start at x equals 0, you want to see what is the error at, let's say, over 1 second versus 0.1. If delta x is 0.1, when you integrate over 10 times, you get 1 second. So after 1 second, if you want to see what the error is, that will be of the order of delta x. If you want to see what the error is over one grid point, so 0.1, if delta x is 0.1, then that would be O delta x square. So it's not a great method, but it's a more widely used method because it has got such a simple formula. And provided this delta x is small, you can really get very good accuracy with this method. So let's just try to see how to use this. And I think the example will make it clear on how this actually works. How do we use the method? So here is a problem on Euler's method. Yes, the problem is, so we're given this ODE dy dx equals f of x comma y equals minus 3y with, I'll write initial condition as IC, y at x equals 0 is 1. Okay, so given that, using a step size equals 0.1, compute the solution for 0x1. So let's do it this way. For 1 by hand, we'll just do it for x 0.3, okay? And using code for x all the way to 1. Yeah, and the reason we're doing this is because when we do it by hand for 3 iterations, we'll check the value if we get the same value using code, and that way we can validate our solution. So let's do it. Okay, so first let's see what the Euler's method is. It's basically this formula. yi plus 1 equals yi plus delta x f of xi yi. Also, we have delta x is 0.1, x0 is the initial value that's here, that's 0. And then we have xi equals x0 plus I delta x. So if you put I equals 0, 1, 2, and 3, we have x I. So x0 will have x0 x0 plus delta x, x0 plus 2 delta x, and x0 plus 2 or 3 delta x, which is basically 0, 0.1, 0.2, and 0.3. You only want to go up to 0.3 by hand. Okay, so that's x. If you like, call it x0, x1, x2, x3. x2, x3. Okay, now the best way I think of doing this, the most easiest way to not make a mistake and to get this through in an exam is to create a table which does the computation for yi plus 1 given yi delta x xi. Okay, so this is what we'll do. Let's create a table of xi yi delta x f of, so this is going to be delta x f of xi yi, but we know what f of xy is. It's minus 3y. So let's just write it down as minus 3 delta x yi. And then our update is going to be yi plus 1 is yi plus delta x f of xi yi. So that will be yi plus 1. Okay, so I'm just going to try to fill this up. And then we'll have our solution in this column, right? We want yi plus 1. Okay, so first we have 0. If you want, you can put I will be 0. We know that the value at x0 is 1. So we just put 1. Next, we compute minus 3 times 0.1 times 1, yi being 1. That's minus 0.3. And then we need to do yi plus 1 is nothing but yi plus this. So you just have to sum up this column with this column. So it's 1 minus 0.3 or 0.7. Okay, so next let's take I equals 1. We want to evaluate 0.1. Okay, now here's the thing. This value now is the value at I plus 1. So it's the value at the next time step. So that value has to be brought down here, 0.7. So once we get it down, we again use this formula. Minus 3 times 0.1 times 0.7 comes out to be 0.49 with a negative sign. So finally, we do 0.7 minus 0.49. It is that right? 7 to the 21. My bad. This should be minus 0.21, I think. 21, and now it's 0.49. Okay, one more step. Let's put 2, 0.2. We have to move this over here. This has moved here. This has moved here. Okay, now we can do 3 times 0.1 times 0.49 equals, I think it's minus 0.147. So this is going to be minus 0.49 minus 0.147 equals 0.343. Okay, so the values which we were after are in this column. So 0.7 is the first value, 0.49, 0.343. I think if you keep the table in this format, that's good enough. So this is one value which is missing, but it's right here. So the first value is 1. Next is 0.7. Next is 0.49. Next is 0.343. With this kind of way it is set up, you always will have this problem where one value will show up on the left side and the remaining values will show up here. Or if you want to go by this 1 point and 0.4 number, it's missing the last value, but that's fine. Okay, so now that we've got this figured out by hand, let's see if we can write code to get the same table. Okay, it's always good to get that table. This is very easy to code, but let me just use ChatGPT because I'm running out of time. So what I would do is, let's make a new chat. Okay, it's a new chat already. And I will just give the same problem, give it as much details as possible. Write Euler's method code for the problem dy dx equals minus 3y with initial condition y is x equals 0 equal to 1 with a step size of dx equals 0.1. And then I might want to specify what I mean by code in Octave. And then the solution should be for x equals 0 to x equals 1. I think I've purposed everything, so let's just see what it does. Okay, so what it's trying to do here is it's trying to put both the parts together. It has a main function, but then it also calls Euler's method loop. This is fine, but I always like to write a function, Euler's method. That way I can reuse that Euler's method for a different function. So let me just tell it to do that. Separate the Euler. Okay, I'll say write a function Euler.m that does the integration and a main file which calls Euler.m. That way I can I just replace the main file with something else, and then I'll still get that code to work, because then it becomes independent of the. So this is generating the Euler method. So it's taking the inputs, the derivative initial value, I think the initial y value x and dx. Okay. Okay, so copy code. Let's go here, paste it to this. Okay, let's save it as Euler. And then let's take the other part. Copy code. Okay, so let's just run this. So it'll make that folder. Okay, now it's easier to save this. It's the same folder, main. Okay, I always like to call CLC close all. So let's see what's going on. So dy dx is exactly what we wanted. Initial conditions is fine, xn is fine, dx is good, Euler, x values, y values. Let's just run this and then we can modify the code. Okay, so this is the plot, which is fine. I close it. This doesn't look like a good presentation of the values. You can see it's giving it as a column. So let's just change it to a row. We don't want it to be printed like this. I can delete this and just say x transpose y transpose. And if you didn't want, you can just make it a little bit beautiful and then see what it does. Okay, so it clips it, but okay, maybe it'll work now. Okay, so here's the answer. So you can check. We had one. Let's see. What I had was, well, 1.7.4.343. All this agrees with the book. Now, if you want it to be in exactly the same form as the form we have, like, column for x, y, dx, then we have to make our own changes. So let's just do that. So what I'm going to do is I'm going to make it output another one called table. This table is the one which I wanted to maybe copy paste into the homework assignment, which will give it in this nice form or help me to check my solution. This table, what I'll do is I will create it. Well, first let me initialize the table and put nothing in it. And then at every iteration, I want to update the table, populating a row in the table. So table equals table. So it's taking the previous value, saving the entire table, and then adding a line to it. And that line should be, for me, it should be, let's see, it should be. So what I want is x, y, this thing, and then yi plus 1. So let's see if I can get that. So there's x is here. Okay, so seems like I need to do x0 plus dx I times this, but I starts from 1, so I need to do this I minus 1. So when I put I equals 1, this will be x0, I equals 2, it will be x plus dx, and so on. So that's first one. Then I need to have yi. Okay, next one. Then I'm going to put this value. And then I'm going to put yi plus 1. Okay, so it produces this table, and then it outputs the table, which I ensured by putting this. Now all I need to do is come back here, and then should be output here. And then I'm just going to comment this out, and then just put disp table. Let's see if it works. Okay. Okay, so this is how we actually had the table. You can check the first 3 lines. So we did have, if you remember, it was, I think I can check here. So it looks good. 3430 is what I got. But you can actually check your calculations here. So this is the good part about this particular, in fact, I've told this many times, but maybe this is one way to illustrate. If you want exam practice, you can create your own problem. Create the problem, solve it by hand, first 3 iterations, and then just run it, and then see if your calculations here match with the calculations in your book. And so you can create infinite problems with this course. You can just create your own problems and check calculations.